Good morning to all of you. We continue with our discussion in electromagnetic induction. You may recall that in the last lecture, I had showed you some demonstrations of Faraday's laws. We saw that if you have a magnet and if you have a coil here, and if you move a magnet towards the coil, there is a current produced in the coil. And if you move the magnet away, the direction of current reverses itself. Similarly, if I fix the magnet and move the coil towards or away from the magnet, there is again an induced current in the coil. We also saw that if I have two coils, in which in one of the coils if I pass current, time varying current, then when the current is varying, there is an induced current in the second coil. Similarly, when I move this coil carrying a current in front of the other coil, there is a current which is induced in this coil. So, all this form Faraday's laws of induction, in which Faraday showed that whenever you have a changing magnetic field, then there is an induced electromotive force in any conducting path. So, this is a very important law in electrodynamics and it is called Faraday's law of induction. So, Faraday's and we also saw that the direction of the current that is passing through the conductor changes as you change the direction of motion of the magnet. So, there is another law which we had introduced, Lenz's law, which says that the direction of current flow is so as to oppose change in magnetic flux. So, when you try to increase the magnetic flux through a closed conducting path, then the conductor, there is a current induced in the conductor which is in such a direction so as to oppose this change. So, if your flux is increasing, then the induced current tries to reduce the flux and keep it as constant as possible. Similarly, if the flux is decreasing, the induced current is in such a direction so as to oppose this reduction in flux, and that is Lenz's law. So, we had seen an example which I will recall now. So, we had considered a conducting loop like this and we had a magnet here. For example, this is the north pole, this is the south pole. We can see the magnetic field direction here, this is coming like this, there is another field line going in this direction. So, these are field lines passing through this conducting coil. So, if I move the magnet towards the coil, towards the conducting path, then the flux through this path increases with time. Now, if I call the area direction as this, remember area is a vector. So, this particular path can be described by an area, this is the area is pointing downwards, the magnetic field is also pointing downwards. So, the magnetic flux defined is greater than 0, and if I move the magnet towards the coil, then the rate of change of magnetic flux with time is positive. So, the flux is increasing with time, flux is positive and increasing with time. So, there is an induced EMF which is minus d phi b by dt, which is negative. So, the induced EMF in this loop is negative, which means that the current induced is such as to oppose this increase in magnetic flux. So, the current that will flow in this loop will be in this direction. So, the current will flow in this loop in this direction, so that it produces the magnetic field which is upwards against the magnetic field of the magnet and tries to control the increase in magnetic flux. So, the direction of the current in this conducting loop is determined by whether the magnet is moving towards the coil, towards this loop or away from this loop. Similarly, if I consider the same loop and if I have this magnet with north pole and south pole and the magnet moves in this direction, in this case again the flux lines, the magnetic field lines are like this, and if I define the area like this again, then phi b is still positive, but d phi b by dt is negative, because as you move the magnet away from the loop, the flux is decreasing with time, and this induces an EMF which is minus d phi b by dt, which is positive. So, in this case the current will flow in the conducting path so as to maintain the magnetic field as before. That means, it will oppose a reduction in the magnetic flux. So, the magnetic field will induce the changing magnetic flux will induce the current in this direction. So, this is the current which is induced. So, that the current in the coil in the loop produces the magnetic field which is in the same direction as the applied magnetic field, and tries to oppose the change in the magnetic flux, the decrease in magnetic flux in the coil in the conducting loop. So, this is essentially Faraday's law of induction. So, essentially the whenever there is a change in magnetic flux through a conducting loop, then there is a current induced in that loop. So, this change in flux could be because the magnetic field is changing with time, or there is a motion between the coil and the magnet, and anything which changes the flux through this conducting loop is going to cause a change in flux, which will cause an induced EMF. So, let me consider an example, a numerical example, to see what kind of EMFs are introduced. So, let me assume there is a magnetic field pointing towards me, uniform magnetic field pointing towards me. So, these are the tips of the arrows which are pointing towards me, uniform magnetic field. So, in this, let me consider a coil, a loop of wire of some radius r. So, I have a uniform magnetic field P, and let me assume that magnetic field is increasing with time. And let me assume that the rate of increase of magnetic field is about 0.04 Tesla per second. So, this uniform magnetic field could be produced by a solenoid. Within the solenoid there is a uniform magnetic field, or by some mechanism I generate a region in which there is a uniform magnetic field, and the rate of increase of magnetic field is 0.04 Tesla per second. Now, let me assume the conducting radius of the conducting loop r is equal to 5 centimeter, and let the resistance of the loop be r is equal to 5 ohms. So, I have a conducting loop of radius 5 centimeter placed in a uniform magnetic field, and that magnetic field is increasing with time. I am, as an example, I consider a radius of 5 centimeters of this current carrying conducting loop, and the resistance of that loop is 5 ohms. Now, what is the induced EMF? Let us calculate the induced EMF. Is equal to minus d phi b by dt. Now, what is the magnetic flux? Magnetic flux is nothing but, because the magnetic field is uniform, the magnetic flux passing through this loop is simply magnetic field multiplied by area. Now, I am going to assume that the area is pointing towards me. So, that it is in the same direction as the magnetic field. So, the area vector of this loop is pointing up towards me. So, the area vector is in the same direction as the magnetic field, and so the magnetic flux is positive and given by B times A, which is equal to B times pi r square. So, the induced EMF is equal to minus pi r square dB by dt. So, this is equal to minus pi. Now, radius of the loop which I have assumed is 5 centimeters. So, 25 10 to the minus 4 meter square into dB by dt. I had assumed a rate of increase of magnetic field as 0.04 Tesla per second. So, this into 0.04, and that is approximately equal to 0.314 millivolt. So, you can multiply and you can find that this is approximately 0.314 millivolt of EMF generated in the coil, in the conducting loop. Now, this EMF will drive a current. Now, because the magnetic field is increasing with time, the area is pointing up. So, EMF calculation must have been like this. So, that the as I mentioned before, the EMF has to be calculated by integrating over the loop. So, because the area is pointing up, according to right hand rule, the integration must be carried out in this direction, and because I find that the EMF is negative, it implies that the current must be in this direction, the current must be flowing in this direction. So, that it opposes, this current will produce a magnetic field pointing downwards, and this magnetic field will oppose the change in magnetic flux because of the increasing magnetic field. So, the current I can calculate, induced current, I is equal to EMF by resistance, which is equal to 0.314 10 to the minus 3 volts divided by 5 ohms, and that is approximately 63 microamperes. So, there is a induced current of 63 microamperes in this loop. So, as you increase the magnetic field with time at this rate of 0.04 Tesla per second, then this magnetic field will induce an EMF in this loop. Because the magnetic field is increasing with time, the induced EMF is negative, and this negative is with respect to integration in this direction. Because this is because I am considering area to be pointing up, the magnetic flux is positive. So, this area is corresponding to a line integral in this direction. So, because the EMF is negative, the actual current which will flow in this direction in this conducting loop. So, this increasing magnetic field will induce a current in the conducting loop, and in this example the current comes out to be about 63 microamperes of current. Now, let me look at another example. Suppose I had a very long solenoid with a coil like this, and let me assume that inside this very long solenoid there is another small solenoid kept. So, let me call this solenoid S1, and there is also a wire in this solenoid. So, this I call S2. Solenoid S1 is the outside solenoid, and there is a current flowing through this. So, this current creates a magnetic field within the solenoid, and because the current is flowing like this, you can see the magnetic field is like this. So, this current carrying solenoid produces a magnetic field in this direction. So, the inside solenoid actually has a flux passing through that solenoid. If I change this current I passing through the outside solenoid, I will change the magnetic field within the solenoid with time. The changing magnetic field within the solenoid will change the flux passing through the inner solenoid with time. The changing flux within the inner solenoid will result in an induced EMF in the inner solenoid, and if the circuit is complete, then it will induce a current in the inner solenoid. So, let me assume that the solenoid, so a very long solenoid S1 with N1 turns per unit length. Let me assume a current through S1 is equal to I1. So, this produces the magnetic field within S1 of let me call this this is mu naught N1 I1, and this is uniform within the solenoid. So, there is a uniform flux passing through the inner solenoid, and let me assume that the inner solenoid, inner small solenoid S2 has a total number of turns of N2 total, and the radius of S2 is equal to R2. So, R2 is the radius of the inner solenoid, and it is carrying a total number of turns N2T, which is equal to the number of turns per unit length of the inner solenoid multiplied by the length of the solenoid. I would need only the total number of turns in this inner solenoid. So, I am just calling it N2T. So, what is the magnetic flux? Per turn passing through S2, which is equal to magnetic field into area, which is equal to mu naught N1 I1 into pi R2 square. R2 is the radius of the inner solenoid. So, the area of the inner solenoid is pi R2 square. The magnetic field produced by the outer solenoid within this within the outer solenoid is mu naught N1 I1. So, mu naught N1 I1 into pi R2 square. So, the total flux through S2. So, each turn has this much flux, and there are N2T turns. So, the total flux will be mu naught N1 N2T I1 into N2T into pi R2 square. So, it is dependent on the total number of turns, because each turn has this flux. So, I multiply by the number of turns in the solenoid, get the total flux. So, I can calculate immediately the induced EMF. Minus d phi b by dt, which is equal to, so the flux is so much. So, this is minus mu naught N1 N2T pi R2 square into d I1 by dt. So, this is the flux, total flux. So, the flux will change if I change the current through the outer solenoid. If I1 changes with time, the flux through the inner solenoid will change with time, and the rate of change of flux is this, which is the induced EMF, which is minus of this is the induced EMF. So, if the outer current does not change with time, there is no induced EMF in the inner solenoid. The moment I change the outer current as a function of time, there is going to be an induced EMF. So, as an example, let me assume N1 is 100 turns per centimeter, a current I1 of 1 ampere. Let me assume N2T is equal to 100, total number of turns, and radius of the inner solenoid to be 1 centimeter. And let me assume that the current I1 changes from 1 ampere to 0 in 10 milliseconds. So, this will give me a rate of change of current d I1 by dt is minus 1 by 10 to the minus 2 seconds, which is equal to minus 100 ampere per second. So, I change the current, I switch off the solenoid and change the current, for example, from 1 ampere to 0 amperes in a time of 10 millisecond, and So, let me assume it is a constant decrease in current as a function of time. So, di1 by dt remaining constant, and that is minus 100 amperes per second. So, the induced EMF is equal to, so I must substitute this. So, this is minus 4 pi 10 to the minus 7, which is the mu naught. N1 is N1 I have given has 100 turns per centimeter, that is 10 to the power 4 turns per meter, into N2t, which is 100, into pi r square, which is pi into r2 square, which is I have assumed a radius of 5 centimeters. So, that is 10 to the minus 4 meter square, into di1 by dt, which is 100 amperes per second. And we can substitute all this and get approximately 39.5 millivolts. So, the inner solenoid has an induced EMF of about 39.5 millivolts. So, that is actually this is a negative sign, there is another negative sign. So, this becomes positive. So, the induced EMF is positive, and that is equal to 39.5 millivolts. So, whenever I change the current in the outer solenoid, I am going to induce a EMF in the inner solenoid, and that induced EMF in this example with these numbers comes out to be about 40 millivolts of EMF, and depending on the resistance of the inner solenoid, and if the circuit is complete, you will have a current flowing through that, and that current will be determined by the induced EMF and the resistance of the inner solenoid. Now, let me look at another interesting example in the same solenoid situation. So, let me assume that I have a long solenoid again. So, this is my solenoid, very long solenoid with current loops like this. Very long solenoid, and let me assume a conducting loop placed outside the solenoid. Coaxial with this solenoid. So, there is a conducting loop here, and this is a galvanometer, just to see the current flowing through that. So, I connect a galvanometer and a coil out and a loop of wire outside. This is a very long solenoid. Now, so this is another example. Now, the question arises as to what will happen if I change the current in the solenoid. The first thing to notice is that the solenoid has, if the solenoid is in principle infinitely long, very long, the magnetic field outside the solenoid is extremely small. It's almost negligible. It's 0 if the solenoid is infinitely long, but otherwise it will be a very, very small value. Now, if I change the current in the solenoid, the magnetic field inside the solenoid is changing with time. But if I look at this outside conducting loop, the flux through that loop is changing with time. So, according to Faraday's law, there must be a current induced in this conducting loop. Please note that if I change the current in the solenoid, the current in the solenoid changing gives me a changing magnetic field inside the solenoid. The changing magnetic field inside the solenoid implies that the magnetic flux passing through this conducting loop changes with time, and according to Faraday's law, there must be an induced EMF in the conducting loop, and so it will generate a current. So, the galvanometer should show me a deflection. Now, in this case there is no moving conductor, so there is no Lorentz force. In fact, the magnetic field itself is almost negligible outside. So, what is happening? Why is there current in the outside conductor? It is simply because a changing magnetic field produces an electric field. So, this changing magnetic field within the solenoid is actually generating an electric field outside, and that electric field is what is driving the current through this outer conductor. Please remember, as earlier I mentioned, it is an electric field, it is not an electrostatic field, because an electrostatic field, the work done in completing one complete cycle from a complete loop is 0, but this one is an induced EMF, electromotive force and so this is generating an electric field which is actually driving the charges. So, this is an example where the changing magnetic field is generating an electric field. So, let me calculate the induced current here. So, let me assume the area of the solenoid is equal to pi r square. So, r is the radius of the solenoid, and so if the solenoid, for a very long solenoid, the magnetic field is equal to mu naught n times I, where n is the number of turns per unit length, and the current is I. The current flowing through this solenoid is I. So, mu naught n I is the magnetic field. So, flux through the conducting loop is equal to B into pi r square. Remember, there is magnetic field only within the solenoid. The loop is much bigger than the solenoid, but there is hardly any magnetic field outside. So, the flux is simply B times pi r square, which is nothing but mu naught n I into pi r square. So, if I now change the current as a function of time, that current changing as a function of time changes the flux through this outer conductor, and that should induce an electric field and an induced EMF. So, what is the induced EMF now? Minus d phi b by dt, which is equal to minus mu naught n a d I by dt. So, this EMF is actually generated in the outer conductor, and so what is actually happening is, as I change my current in the solenoid, the magnetic field is changing with time, and a changing magnetic field is generating an electric field outside, and that is that electric field which is driving the current through the outside conductor. And so, if I define the EMF as integral E dot dl. So, if the EMF is defined as the work done in taking unit charge across one full revolution here, and that is integral E dot dl. So, this is an electric field and not an electrostatic field, and this is equal to minus d phi b by dt, which is equal to minus mu naught n a d by dt. So, this changing current in the solenoid is actually generating a changing magnetic field, and that changing magnetic field is inducing an electric field outside in the conducting loop. Now, let me try to estimate what is the electric field produced by this changing current. So, for this, let me draw this same figure, cross section of this figure, let me draw. So, this is my solenoid, and let me assume that the magnetic field is pointing inwards, uniform magnetic field pointing inwards, and my conducting loop is outside. So, let me draw the conducting loop, concentric with this, that is the conducting loop outside. So, for d I by dt greater than 0, if you look at this, for d I by dt greater than 0, induced EMF is negative. EMF is negative. Now, please remember, the magnetic field is pointing downward. So, if I have defined the flux as positive, the integration loop must be in this direction, because the magnetic field is pointing downward. In E is equal to, in this equation, E is equal to integral E dot dl is equal to minus d by dt of integral B dot dA. This is the magnetic flux, rate of change of flux minus rate of change of magnetic flux is EMF, which is integral E dot dl. So, this is over a path C and this is over an area A. So, there has to be consistency between the definition of the path C, in which direction should I integrate, and the area. So, if I call the area downwards as positive, the integration must be in this direction, and because the integration is this direction, and if the current increases with time, induced EMF is negative, that means the electric field must be pointing in the in this direction, as I will show you. So, electric field at this point, this electric field must be pointing in this direction, in the other direction. So, that integral E dot dl becomes negative if I integrate like this. If I integrate like this, because that is the direction of integration, I must get a negative value. So, the electric field must be pointing in the opposite direction. Now, remember in my earlier lectures, I have used symmetries to estimate the directions of the fields, electric field in terms, electrostatic field in when we were discussing Gauss's law, magnetic field direction in the case of Ampere's law, and I want to again use some symmetry here. The first thing is, because the solenoid is assumed to be infinitely long, the electric field has to be, cannot have a z component, cannot have a component like this, it must be in this plane. It has to be independent of this angle, because it has to be the same in all orientations here, because the system is completely symmetric. So, the electric field here, here, here at a given distance from the center must be exactly the same. Also, it cannot have a radial component, because if it had a radial component, then it will imply, according to Gauss's law, that there are some charges inside, and I know there are no charges inside, no positive charges. If there are positive charges, it will give me an electric field outward direction, and because there are no charges here, electric field cannot have a radial component. So, it must have only an azimuthal component. That means, electric field must be pointing like this point like this, here is like this, here is like this, here is like this, here is like this. So, this is the electric field direction. Look here, I am using some symmetry arguments to say that the induced electric field, because of the changing magnetic field, must be in this direction. Because of symmetry, it cannot have a z dependence, electric field has to be in this plane, it cannot have a radial component according to Gauss's law. So, it has to be a component which is like this, and so, and it is the same at all points. So, this I can immediately integrate. So, integral E dot dl is equal to 2 pi into, if this distance is r into e, 2 pi into r into e, and that must be equal to minus mu naught N A d I by dt, which is the rate of change of flux. So, the electric field induced is actually minus mu naught N A by 2 pi r d I by dt. Very interesting, because this electric field, which is induced by the changing magnetic field within the solenoid, will now push a charge in this direction, and that will induce a current. If there was a conductor here, it will induce a current, and that current will flow like this, and that current will try to oppose the change in the increase in current. So, if the current is, if the di by dt is positive, then the electric field will be like this. If I di by dt is negative, the electric field reverses itself in direction. So, please let me redefine again. In the induced EMF, it is called an electric field. In this case, integral E dot dl is not equal to 0. For electrostatic fields, integral E dot dl is equal to 0. So, this is a different, this is an electric field, that is why I am calling it an electric field, and that field is exactly this, similar to electrostatic field. It has the same force on a charge q e, but that electric field is what is called as non-conservative. That means, that integral of E dot dl is not equal to 0. So, let me calculate some value here. So, for this example, so r, small r is the radius of the solenoid. So, let me assume as an example number of turns per unit length N is equal to 1000 per meter. Let me assume dI by dt is equal to 100 amperes per second. Area of the solenoid is equal to pi into 25 10 to the minus 4 meter square. I am assuming a solenoid of radius 5 centimeters. So, and I want to calculate. So, this radius is 5 centimeters, and I want to calculate a distance of 10 centimeters from the center of the solenoid. So, I want to calculate what is the electric field induced electric field at r is equal to 10 centimeter. So, I want to use this equation which we have derived. This is the equation. So, let me rewrite it again here. So, E is equal to minus mu naught n times A by 2 pi r dI by dt. So, let me substitute the numbers. Minus 4 pi 10 to the minus 7 into 1000 turns per meter into area of pi into 25 10 to the minus 4 meter square. dI by dt is 100 amperes per second divided by 2 pi into capital R is 10 centimeter, that is 0.1 meters. And we can calculate this. This comes out to be about 1.57 into 10 to the minus 3 volts per meter. So, well, with minus sign here and this sign essentially. So, the direction of the electric field one has to remember, and this is the magnitude of the electric field is about 1.6 millivolts per meter. So, this changing magnetic field within the solenoid is actually causing an electric field to be generated outside. In fact, it is generated everywhere. Whatever the distance is, you will have an electric field generated. So, this is a very interesting situation where a changing magnetic field generates an electric field, and this electric field is different from an electrostatic field. So, it can do work, and this electric field is actually leading to an EMF, and that EMF is responsible for driving a current in a conducting path. So, these were some examples of Faraday's law of induction, which showed me that a changing magnetic flux through a conducting path will induce a current through that, an EMF, induced EMF, which if the path is conducting, then it will lead to a current in the conducting path. Now, please note that even if I do not have a conducting path, I will still generate an electric field, an EMF in any chosen path that you want to integrate, and that induced EMF will depend on the flux, rate of change of flux through that path. So, as we have seen in the earlier example, in this case of the solenoid and a path outside, in this case of a solenoid which is like this and the magnetic field is like this, at this point there is an electric field irrespective of whether there was a conducting coil or not, which means that this electric field will be generated in space. A changing magnetic field will generate an electric field in space, and that electric field can lead to a current if there was a conducting path. So, if there was a conductor here, this will lead to a current going like this, and if there is no conducting path, there is still an electric field that is generated in space. So, this is a very, very important law in electrodynamics, that a changing magnetic field can generate an electric field. Now, these are examples in which the EMF is generated simply by changing the flux of the magnetic field. Another kind of EMF which is understood in terms of Lorentz force is called motional EMF. Let me take an example of a motional EMF. So, let me take a magnetic field pointing downwards, uniform magnetic field pointing downwards. So, these are the ends of the arrows. So, magnetic fields are pointing down and uniform. Now, let me take a conductor like this and move this in this direction. So, this is the conductor, this conductor, straight conductor, I am moving the magnetic field like this. Now, what is going to happen? There are electrons in the conductor, and because the when I move the conductor, the electrons start to move. Motion of the charge in a magnetic field will induce a Lorentz force on the charge. So, an electron moving like this with a magnetic field pointing downwards, V cross B is upwards, V cross B is upwards, but because the electron has a negative charge, the force is downward. So, Q V cross B is the Lorentz force, V cross B is positive, Q is negative. So, Q V cross B is downward, and so what will happen is the electrons will be pushed towards the downside toward this end, leaving a net positive charge on the other side. So, there will be a negative charge here and there will be a positive charge here, net positive charge. And this motion, if I continue to move at a constant speed, then the charges will accumulate in such a fashion that once the charges have accumulated, these charges will generate their electrostatic field, and that electrostatic field will be such that it will compensate for the magnetic force. So, the force due to the electrostatic field will be equal to the force due to the magnetic field, and then no more charge motion will take place. So, so what is the force on the what is the Lorentz force? Q B cross B, and because V and B are perpendicular, this is nothing but Q V B, and the electric field which will be generated will be such that Q times E will be equal to Q V B. That means, it will generate an electric field given by Q is equal to V B, and this will generate a potential difference between the ends of, if this length is L, B B L. So, there will be a potential difference between these two ends, which will such that if I keep moving with this constant velocity, then this potential difference will generate an electrostatic force, electric force on the charge in the upward direction, and in the upward direction, magnetic force in the downward direction, and these two forces compensate. So, this is simply a result of Lorentz force. Now, let me modify the problem a little bit further. So, I again draw a uniform magnetic field pointing downward, represented by these crosses. And now, what I do is the following: I place another conductor like this. I have a conductor like this, and place this conductor which I am moving on this conductor. So, this is the length L, which I was mentioning before, and this is moving like this. Now, as I move this conductor to the right, electrons are exerted upon by a magnetic force. So, electron motion is like this, field is pointing downward. So, V cross B is upward, Q V cross B is downward, and the electrons will come here. Once the electrons come here, there is a net negative positive charge left here. So, the electrons can now flow through this path and come back here, and as they arrive here, they are again pushed down by the magnetic force, and they constitute an electron flow like this, which implies that there is a current flowing in this loop in this direction. So, this can be seen by a simple argument of Lorentz force, that as I move the conductor in the magnetic field, the electrons in the conductor suffer a magnetic force, and that magnetic force leads to a movement of this electron through the conductor, and that conductor leads to then this moving electrons constitute a current. Now, I can picturize this from a different perspective. According to Faraday's law, when I move this conductor in front of this, I am changing the area of this conducting path, and as I change my area of the conducting path, I am changing the magnetic flux through this conducting path, and I know that a changing magnetic flux leads to an induced EMF. So, please note this in this argument in Faraday's law, using Faraday's law, as I move this conductor to the right, I am changing the area. So, if I am here, I have this area, if I am here, I have a little more area, if I am here, I have more area. So, as I move my conductor to the right, I am increasing the area of this conducting path, and as I increase my area of the conducting path, I increase the magnetic flux through the conducting path, and a change of magnetic flux leads to an induced EMF. So, in this path I must see an induced EMF, and once there is an induced EMF, that will lead to a current. Now, let us see what happens. So, if I move to the right, I am increasing the area with time. So, if I were to look at area vector downward, I am increasing a magnetic flux with time. So, induced EMF must be negative. So, if I move like this, because the area is pointing downward, the EMF calculation must be in this direction. So, I must look at the EMF direction like this, but EMF happens to be negative. So, induced EMF must be like this, which will induce a current in this direction, exactly like what we have got from Lorentz force. From Lorentz force, as I move this conductor, electrons in the conductor are pushed down, and they then constitute a current through the conducting loop. So, as I move here, the conducting loop, there is a current flowing through the conducting loop because of Lorentz force. The other interpretation is, equivalent interpretation is that as I move my conductor to the right, I am increasing the magnetic flux through this area. If I define my area as downward, magnetic flux is positive. So, the magnetic flux increases in magnitude with time, and it is also directed downward. So, to be consistent, my EMF calculation must be in this direction. So, because d phi by dt is increasing with time, EMF induced is negative. So, if I integrate like this, I get a negative value of EMF, that means the current must be flowing in this direction, exactly like from Lorentz force. So, what is the so let me assume that the resistance is R. So, let me assume that this part of the conducting path has almost no resistance, and it is primarily this path. So, as I change my area, the resistance is assumed to be remaining constant. So, I am assuming that only this part of the conductor has resistance, the remaining part of the conducting circuit has almost negligible resistance. So, the resistance is R. So, the current induced is equal to EMF by R, and EMF we have just calculated. EMF is V times B times L. So, this is equal to V B L by R. Now, there is a current flowing through this conductor in this direction. So, now what happens? When I am moving the conductor, I am now moving a current carrying conductor in a magnetic field. My movement of the conductor induces a current in the conductor, induces a current in the entire circuit. This part of the conductor is now moving, and I know that a current carrying conductor has a magnetic force acting on it. So, what is the magnetic force? On the current on the moving conductor? I L cross B, L is the length, and because L and B are perpendicular to each other, this is nothing but I L B, and I have calculated. So, this is equal to B square L square V by R. That is the magnetic force on the current carrying conductor. So, what is the direction of the magnetic force? So, the current is now flowing like this. So, L cross B, the force is magnetic force is towards the left. It is, so I am trying to move the conductor to the right, the magnetic force is pulling it to the left, and this is exactly what is happening because of the induced direction of the current. So, the current, induced current, is so as to oppose the change which I am trying to do. So, if I have to pull the conductor, I must do work against this magnetic force on the current carrying conductor. The other parts of the conductor are not moving. So, this is the one which I am trying to pull. When I am trying to pull this conductor, there is a current in the conductor, there is a magnetic force on the conductor, and that magnetic force happens to be to the left. I am trying to pull it to the right. So, I must do work against this magnetic force. So, let me calculate what is the work done per unit time. This is equal to force into velocity, which is equal to, so the force is b square L square v by r. So, b square L square v by r into velocity, which is equal to b square L square v square by r. So, this is the work that I am doing per unit time in pulling this conductor. So, here is my conductor, and if everything is at rest, there is no induced current. The moment I start to move it, if I start to move it, because of Lorentz force or because of Faraday law of induction, you can use either of them, you find that there is an induced current in the circuit. The induced current direction is like this, which you can interpret either from Lorentz force law or from rate of change of magnetic flux. So, you have an induced current like this. So, on this wire, which I am on this conducting rod which I am trying to move, there is a current flowing in this direction. So, the current carrying conductor has a magnetic force. We have seen earlier that if you have a current carrying conductor in a magnetic field, there is a force on the conductor, and for a length L, the force is simply given by I into L cross B, current into L cross B, and that force, because of the direction of the current, the magnetic force is towards the left. So, what is happening now is I am trying to pull it, my pulling induces a current, that current then is acted upon by magnetic force pulling it towards the left. So, I have to do work against this magnetic force, and so the work which I am doing per unit time is simply given by b square L square v square by r. Now, because there is a resistance in the circuit, if you have a current I passing through a resistance, we have seen that there is a Joule heating. That means, if you have a current I in a resistance R, the power consumed is I square R, square of the current into resistance. So, we have calculated the value of the current V B L by R. So, I get V B L by R whole square into R, which is nothing but B square L square B square by R, exactly the same as the work that I have to do to pull the wire. So, what is actually happening is the force that I am applying to pull the wire to the right is being used up for heating the conducting path through the Joule heating. So, I need to do work, and this is a very interesting example of how the work that I am doing on moving the conductor is being used up in Joule heating. So, this was an example in which I could employ either Lorentz law, Lorentz force law to calculate to show there is an induced current, or the magnetic Faraday's law of induction. But please remember, there are other situations where nothing is moving, and a change in magnetic flux or changing magnetic field through another mechanism can lead to an induced EMF, and that is the most general form of Faraday's law. So, we will continue with discussion on Faraday's laws of induction in the next class. Thank you very much.